So we are going to continue with our next video presentation entitled Geometric, Physically Based and Numerical Simulation of NC Grinding Processes for the Calculation of Process Forces. This contribution is from our colleagues from the Institute of Virtual Machining at the Technical University Dortmund in Germany. The authors are Mr. Wöste, Mr. Siebrecht, Mr. Fast, and Mrs. Wiederkehr. We are looking forward to your video presentation.
Hello, my name is Florian Wöste and I'm a research assistant at the Technical University of Dortmund. Today I would like to present some recent results about the geometric, physically based and numerical simulation of NC grinding processes for the calculation of process forces by taking the individual grains on grinding tools into account. NC grinding processes can be used for different applications, such as finishing of free-form forming tools. Since the material flow in the forming operation can be influenced by local surface roughness, time-discrete simulations of the grinding process can be used to predict the properties of the resulting surfaces. By modeling the geometric shape of the individual grains on the grinding tools, the surface topographies can be calculated. These are influenced by process effects like tool wear, which has to be taken into account in the simulation. The wear-dependent model of the grinding tools was created by analyzing measured topographies of grinding tools in different states of tool wear. The measurements of the grinding tool topographies were conducted using confocal white light microscopy. Using a binary mask, the individual grains were separated. It was created using watershed segmentation algorithm with a consequent manual refinement. Each of these grains was modeled by a point cloud with approximately 200 points, resulting in a database of representative grain shapes. By distributing instances from this database randomly on the macroscopic surface of the tool, arbitrary tool shapes can be modeled using the same database without conducting further experiments. In order to obtain uniform distributions of the grains on the tool model, Poisson dissampling was used, based on the geodesic distance on the macroscopic surface of the grinding tool. Here, you can see an example of a random distribution of 3,312 diamond grains on a cylindrical grinding tool. Please note that each grain is modeled by a point cloud. Since the grain database contained only about 80 representative grain shapes, each of these point clouds was used multiple times. Based on the described tool model, the initial workpiece surface, and the NC program, the grinding process was simulated by modeling the workpiece as an height field. In time-discrete simulation steps, each individual grain was intersected with this workpiece height field. By subtracting these intersections from the workpiece height field, material removal was modeled. The intersections correspond to the undeformed chip shapes of the grain engagements, which were analyzed to calculate the process forces. The details of this process simulation are described in the following slides. The intersection between the moving point cloud of a grain and the workpiece height field was calculated by describing the sweep volume of the grain in the current simulation step. Since fixed time steps were used in the simulation, the distance between the grain at the beginning of a simulation step and at the end of a simulation step can cause gaps as seen in this example. Therefore, The point cloud of the grain was instanced at additional discrete substeps. The resulting point cloud of the sweep volume was projected onto a sweep height field, which had the same resolution and alignment as a workpiece height field. Due to the inhomogeneous resolution of the point cloud, resembling the sweep volume, morphological filtering operations were used to interpolate between the points. Material removal was simulated by subtracting this sweep height field from the workpiece height field. Here you can see a video of the described simulation system, which can be used to predict the resulting surface topographies based on the individual grain engagements. The grains currently in contact with the workpiece are highlighted. In the detailed view, you can see the point cloud models of the grains as well as a height field of the workpiece surface. In order to calculate the process forces, the undeformed ship shape of each grain engagement was analyzed. Using an empirical process model, the process forces were calculated based on the undeformed ship area. For the purpose of determining the undeformed ship area, the height field segments removed from a grain in a simulation step were projected onto a plane. The normal vector of this plane corresponds to the direction of the cutting velocity of the grain, as you can see in this illustration. The undeformed ship area was calculated as the sum of the differences between the minimum and the maximum vertical coordinates in the coordinate system of the projected plane, which corresponds to the resulting green area shown in the slide. The empirical process force model can be calibrated by determining the correspondence between the undeformed ship area and the process forces using single grain scratch tests. Here you can see the experimental setup based on a rotating workpiece and a fixed diamond grain on its grain holder on a turn milling machine. The workpiece material used was AISI D2 tool steel. A helical scratch with an increasing depth of cut was created, and the forces acting on the grain were measured. The resulting scratches were analyzed to determine the undeformed ship areas and their corresponding process forces. However, the experimental effort is quite high, and the maximum depth of cut is limited by the wear of the diamond grain. Therefore, a numerical process model was used to analyze individual grain engagements. The coupled Eulerian Lagrangian method, which is implemented in the commercial finite element software Abacus Explicit, was used as the modeling approach. Thereby, the grain was assumed to be rigid, while the model of the workpiece was described by an Eulerian formulation. Within the fixed Euler domain, the workpiece material was assigned to a predefined field and could move through the mesh due to an interaction with the grain. As you can see in the illustration of the process model, the surrounding region of the grain engagement was discretized by a fine mesh, while distant parts of the Euler domain were meshed more coarsely in order to reduce computing time. The cutting motion was carried out by the grain and is based on the cutting speed used in the experiment. In order to characterize the material behavior during the grain engagement, a coupled thermomechanical analysis was conducted and the constitutive law by Johnson and Cook was applied. In order to describe friction effects during grain engagement, Coulomb's law was used with a coefficient of friction of 0.15. The grain used in the experiments was previously digitalized using confocal white light microscopy, and a mesh was generated as a result. In order to determine the correspondence between the uniform ship area and the process forces, both were analyzed as soon as a stationary engagement was reached. For the selected interval, the mean forces in cutting direction, which is parallel to the y-axis, and in normal direction, which is parallel to the z-axis, were calculated as well as the corresponding uniform ship areas. The cutting force coefficients were then calculated as a ratio of force to uniform ship area. With regard to the experimental results, the uniform ship thickness was varied between 0.5 and 5 micrometers, resulting in a total of 7 different grain engagements. The cutting force coefficients were determined for each process simulation conducted. Here you can see a video of the described numerical process simulation. The material behavior during the grain engagement is highlighted using the occurring Fomesis stresses. The uniform ship thickness in this process was 4 micrometers. The forces acting on the grain amounted to 9.2 Newton in normal direction and 3.8 Newton in cutting direction. The resulting uniform ship area was 236 square micrometers. Based on the results of the numerical simulation, the process force coefficients in cutting and normal direction could be determined by regression analysis as a function of the uniform ship area. A comparison of the experimentally and numerically determined coefficients, depicted on the right side of the slide, shows a sufficiently accurate approximation of the numerical model for uniform ship areas between 38 and 95 square micrometers. Only for very small areas a significant deviation in normal direction occurs. Generally, the correlation between the force coefficients and the uniform ship area shown in first experiments could be reproduced using the presented numerical model. Therefore, complex single-grain cutting experiments to calibrate the empirical force model can be avoided. To conclude my presentation, I would like to show some validation experiments, which we analyze using the presented simulation system as well as the process force coefficients predicted by the numerical model. A grinding tool with D427 grains and a diameter of 15 mm was used for this purpose with a cutting velocity of 10 meters per second and a feed velocity of 800 mm per minute. The radial depth of cut was 15 micrometers and the axial depth of cut was 4 millimeters. While significant noise was present in the simulated and measured process forces, due to the high amount of grain engagements, a low-pass filter comparison shows a good correspondence between simulation and experiment, and thus the applicability of the presented approach. Thank you very much for your kind attention.
Thank you for sending us your video presentation. We have been just watching the presentation entitled Geometric, Physically Based and Numerical Simulation of NC Grinding Processes for the Calculation of Process Forces from our colleagues from the Technical University Dortmund in Germany. And our presenting and discussion author is now Tobias Siebrecht. Tobias, can you hear us?
Yes, I can hear you.
Great. There are some questions regarding your paper, so I'm going to just read them to you and then would like to ask you to answer those. The first one is, the commenter has written that you have mentioned in your paper the predicted process forces y direction were slightly lower than the measured forces, but a good correspondence was still achieved. What does the difference mean for the process and the result? And what can be done to achieve better results?
Okay, yeah, first of all, thank you very much for having the opportunity to present our research on this conference. And regarding the results, the calculated process forces, there was a slight deviation in the y direction. And we have analyzed the mean value of the process forces and compared the measured values to the simulated results. And in the experiments, we had an average process force of 6.05 newtons in y direction. And in the simulation, it was 5.31 newtons. So that's a deviation of about 13%. And the experimental process forces were slightly higher. But this deviation is not that high when taken into account the assumptions that were made when parameterizing the simulation system. The numerical simulations have been carried out with one representative diamond grain shape, and the rake angle, for example, was neglected. So in future investigations, we could extend these investigations with additional shapes of diamond grains to probably achieve a better correspondence.
Thank you for your answer. I'm going to continue with the second question. This is, what are the potentials of your approach for possible industrial applications?
Okay, so I think there are several potential applications in the industry, and we have to take a look at what can be calculated with our simulation systems. On the one side, we are able to predict the surface topographies resulting from different grinding processes. So one potential application would be the design of a new grinding process or new grinding tools for a specific surface topography which has to be achieved in the grinding process. And the other aspect would be the process forces. One application could be the calculation of these process forces and the prediction of process vibrations in order to avoid chatter vibrations in grinding processes, for example.
Okay, thanks a lot. And my last question is, since one of the recent questions which we are focusing on within the CIRP community is the environmental impact of any processes. What do you think for grinding? What is the environmental impact of the research in grinding, and especially your approaches within your projects?
Okay, so I think that one very important aspect regarding the environmental impact is the use of the cutting fluids, for example, in grinding processes. And one possible application of our specific simulation system would be to take the influence of the cutting fluids into account in order to minimize the amount of cutting fluids required in a grinding process, for example. So I think this could be one important contribution to a more sustainable grinding process.
And do you have it on pipeline to work on these aspects?
Yes, it's future research. So we are trying to couple our simulation approach with cutting fluid simulation in order to take this influence into account.
Thanks a lot. We are going to follow your future works and publications. Thanks also for your time, for
Thank you very much.
being here, and hope to see you soon. Bye.
Goodbye.